So Sommerfeld elaborated on Drude's very simple model in a number of ways. Let's begin by deriving some useful quantities from this model of free electrons. So the first thing to ask is what is the electron density? And the number of electrons will be given by 2 if we put spin up and spin down into each k-state, times the integral from 0 to some highest occupied k-state, the Fermi wave vector kf. This is just the largest, highest, corresponds to the highest energy that's actually occupied, times the number of states per unit k, which we derived in chapter 2, so this then integral of k squared to k brings out a k cubed over 3. The 2's cancel, and the answer is kf, when you insert the limits, cubed over 3 pi squared v. Now remember, I told you when we did periodic boundary conditions that in fact the choice of L, and remember v here is L cubed, doesn't matter. And the reason is what we're really interested in is this quantity, the electron density. And so at this point, our L cubed drops out, and we arrive at this very simple result. So alternately, we can write down that Kf is the cube root of 3 pi squared n. So with this definition of the Fermi wave vector, the highest occupied state by electrons then, the Fermi energy, which is just h bar squared kf squared on 2n, can be written as a function of n by substituting this expression here. The Fermi velocity, so this isn't a volume, this is the velocity of electrons at the Fermi energy, is given by their momentum, h bar kf divided by m. So in this table, I show you quantities derived from this model of free electrons, taking a density of free electrons for lithium. It's a 1 electron metal, so we've just taken the density of lithium and multiplied by 1 electron. Units are in electrons per cubic centimeter. You see the Fermi wave vector corresponds to around about 1 over 1 angstrom. So the wavelength of electrons is approximately atomic at EF. So the electrons that are free to move in a solid because they're near the Fermi energy have very short wavelengths indeed. Look at their Fermi velocity. It is absolutely enormous. We have Vf is round about 10 to the 8 centimeters per second. This is a non-trivial percentage of the speed of light, which is actually 10 to the 10 centimeters per second. And so electrons are not moving with thermal velocities at all, but the exclusion principle just requires that the electrons closest to the top of the states that are filled have an enormous velocity, which is why, by the way, the mean free path was wrong in the Drude model. And then finally, we have an expression for the Fermi energy, and we see, as I have asserted many times, that EF is around about 5 electron volts. There's one extra interesting thing that comes from this analysis. Let's do a calculation of the average energy of electrons. To do this, we are going to integrate h bar squared k squared over 2m, that's the expression for the energy as a function of k. We're going to multiply by the volume element in k, so 4 pi k squared dk, and we're going to integrate this from the lowest state 0 to the highest state kf. So you see we have a k to the 4th, which integrates to give you k to the 5th over 5, and the net result then is that the average energy is h bar squared over 10 pi squared m k to the fifth. Now, recalling the relationship between, kf, that was the upper limit of the integral. Recalling the relationship between kf and n, you can see that we can write the average energy as being proportional to n to the 5/3. This was exactly the result I quoted in Chapter 2 for the kinetic energy functional, where we used, now this of course is for a free electron gas with a uniform energy density, we used the expression n to the 5/3 where n was a function of r. Incorporating the distribution of electrons explicitly has an important result in the Sommerfeld model. Here once again is the Fermi-Dirac distribution, and for all sensible values of temperature, the fraction of electrons that's excited is very small. That's something I referred to earlier. So the average thermal occupation in a single particle state versus temperature, or energy rather, where this was the Fermi energy, looking like this at 0 temperature, and then broadening out at finite temperatures. Just approximately, this area here is proportional to kT, whereas this area here is proportional to EF. So the fraction of carriers available to carry out transport then looks like approximately kT over EF. So when we calculate transport properties, we need to multiply what we think the free electron density is by this factor kT over EF. So this reduces the conductivity over what might be expected for a free electron gas given the density of atoms. It means that other transport properties like the specific heat are similarly reduced. It also has a very interesting consequence. The specific heat at low temperatures turns out to be proportional to temperature purely because of this factor here. So now we understand a lot about transport in free electron systems, but we still haven't answered the question of what controls the number of electrons available for conductivity, and why is a rubber 23 or 24 orders of magnitude less conductive than silver? We turn to that question in the next module.